Where a live conductor or a spinning shaft has to pass through a metal wall, the two must never touch. A single point of contact means a short, an arc, or a seized bearing. The white flanged sleeves turning here solve it quietly. Each one lines the opening, seats on its flange, and holds whatever runs through it perfectly isolated and perfectly centered, in heat and voltage that would defeat ordinary materials. Its first task is to insulate. High-purity alumina is an outstanding dielectric, holding a breakdown strength on the order of 17 kV per millimeter and a volume resistivity above 10 to the 14th ohms centimeters, so current that would jump a gap simply cannot cross it. It also runs with very low dielectric loss, so it stays cool and stable under a steady electric field instead of heating from within. Temperature barely troubles it. Alumina keeps its strength and its insulation up to around 1,600 degrees, far beyond where polymers char and metals soften, so a bushing can sit in a furnace wall or beside a heating element without losing its grip or its isolation. It carries that heat steadily and returns to size as it cools, holding its dimensions cycle after cycle. Strength rounds out the picture. With a hardness many times that of steel, the bore resists the wear of a turning shaft or a threaded rod without scoring, and the dense, non-porous body shrugs off acids, solvents, and damp atmospheres that corrode metal fittings. Nothing soaks in and nothing wears away, so the fit it leaves the workshop with is the fit it keeps. These abilities are written into the chemistry. Aluminum and oxygen bond into a dense corundum lattice with their electrons locked firmly in place, which is exactly why alumina insulates so strongly and resists heat and chemical attack. Pushing the purity upward, often past 99%, sharpens every one of those traits at once. Cleaner grains, higher strength, and a more reliable dielectric. Two finer details decide how well it serves. Fired to full density, high-purity alumina is effectively non-porous. So no moisture or contaminant can creep in to track a current across its surface. A glaze is barely needed. And its dielectric loss runs far lower than porcelain or steatite, several times lower, so under high voltage it wastes little energy as heat and ages slowly rather than degrading. Sizes start from the hole the sleeve has to line. Bores run from a few millimeters for a thin conductor up to tens of millimeters for a heavy shaft. The body length is set by the wall it crosses, and the flange diameter is sized to seat squarely against the housing. Faces and bore are ground to a close tolerance so the part slides home and registers without play. A stepped or shouldered flange to locate it, a plain or threaded bore to match the part it carries, chamfers and grooves for seals or retaining rings, and an alumina purity chosen for the voltage and temperature. Where it must join metal, the sleeve can be supplied already fitted into a housing or assembled with gaskets and hardware. A common home for this part is the electrical feed-through, where a live conductor must pass through a grounded wall or panel and reach the other side without losing a volt to the frame. There, the flanged alumina sleeve seats in the opening and carries the conductor through, blocking breakdown across its wall while the flange seals and locates it against the housing. It holds that isolation as the equipment heats and cools, stays dry and uncontaminated in damp or dusty air, and keeps its precise bore so the conductor never shifts. A porcelain part might track or crack over time, but this one ages slowly and quietly. Decisively, the smallest component bridging the wall is the one that keeps the power on the right side of it.